All right, section 10.8 is on similar solids. We've talked about similar triangles before. And what made two triangles similar? Angles were the same. Sides were proportional. That means they're the same shape, but bigger and smaller. That's what happens with similar solids as well. Your similar solids, if you look at these two cubes, they're the exact same shape. They're the same shape, but they're a different size. So different size makes it a similar figure. It also, they should have the same angles, and they have to have proportional lengths. And that means all lengths are proportional. All lengths have to be proportional. Not just one or two of the sides. All the sides have to be reduced to the same ratio. Now let's look at the theorem for similar solids. It just gives us some ideas on things. It says if two solids have a scale factor of A to B, so your scale factor is A to B. If you want to find the area ratio, you just need to square it and get A squared to B squared. If you want to find the volume ratio, you need to cube them and do A cubed to B cubed. We're going to use that information on the next couple of slides to solve for some of the pieces. So I'll give you a few minutes, or a minute or so to get that copied down so you have it, and then we'll move on. These go pretty fast. There's not a lot of examples in these, and their examples do go pretty quick. So you will probably have some time in class to start your practice problems so that you may not have too much homework tonight at all. Surface area is always measured in square units. So we would square it to get the scale factor. And volume is always measured in cubic units. So we would cube them to get the volume ratio. Okay, I'm going to move on so that we can get going. I can come back to this later if you need it. Okay, now first example is just asking us the question, are these two solids similar to each other? For them to be similar, all the sides have to reduce to the same ratio. All corresponding sides. So this 3 corresponds to that 6. This 2 corresponds to that 4. And this 2 corresponds to this 2. Do they all reduce to the same ratio? No, these first two reduce to a half. This one reduces to 1. So that's not equal right there, so that is definitely a no, not similar. So that's A. That's how we can tell if they're similar or not. And you can kind of tell they're a different shape because one doesn't go in proportion to the other ones. Now in this one you've got 4 corresponds to 2, so you could put 4 over 2. You could do 6 corresponding to 3. And this 4 corresponds to that 2. So all of these are going to reduce to 2. What that tells me is that they are similar. They're not congruent, they're similar. You can tell that one is smaller than the other, but they are the same shape. Got just like a miniature version of the big one here is what that is. So those are similar. That would be yes. See, like I said, most of these examples, they move pretty quick. So they'll go fast. Ready for the next one? Okay, this one says the following two prisms have a scale factor of 1 to 3. I'm going to put that over here. SF is going to stand for scale factor, and it's 1 to 3. That's going to be important. We're going to need that. Now it says find the surface area and volume of prism G. Okay, so we're going to be looking for the surface area and the volume of this prism right here. Given that the surface area of prism F is 24 square feet and the volume of prism F is 7 cubic feet. So if my surface area or my scale factor is a 1 to 3 ratio, what's my area ratio have to be? 1 squared to 3 squared, which would be what? 1 to 9. So my area ratio has to be a 1 to 9 ratio. That means the surface area of the one has to be 9 times bigger than the other one. The bigger one is 9 times greater than the smaller one as far as surface area. What does the volume ratio have to be? 1 cubed to 3 cubed would be 1 to 27. Now, if you're not sure how I got these numbers, this would be 1 squared to 3 squared. This would be 1 cubed to 3 cubed. That's what we learned back on this very first slide, that you square it to get the surface area and you cube it to get the volume. So that's what I did. Now, those are going to be important. I need those because I need to solve for the surface area. So what I've got right now is I know that the area ratio is a 1 to 9 ratio. And my two solids have to be a 1 to 9 ratio. And I know that the top one's, the little one's 24. So I need to know what could I put in here for x that would reduce to a 1 over 9 ratio, because it has to reduce to that much. So how do I solve something like this? Just cross multiply. You're going to get x equals 9 times 24. So your surface area of the big one is going to be just the 9 times the 24, which is 216. Yes. And that would be in square feet. So that's how you do the area ratio. What about the volume ratio? What do we have to have for volume? Has to reduce to what fraction for volume? 1 over 27. I already know that my little volume is how much? Little volume is 7. So I need to find my big volume. Do this. All right, so what we need to do is find the volume of the big one. So you're going to do your 1 times x is x. Your 27 times your 7 comes out to be 189. So the volume of the small one would be a 7. The volume of the big one would be 189. That means 27 of these little ones would fit inside of this big one. That's how the volume would correspond to each other. Okay, moving on to the next one. Okay, find the scale factor of the two cubes. Scale factor. Okay, so let's see if these are all x's. How could I solve for x here? If I know that x times x times x, these three x's together multiplied to give me 512. That means 512 is going to equal x cubed. How do I get x? Cube root it. So the third root. And if you do in your calculator, you put the 3 in first, then you hit that little button with the square root and the x there, and you put in the 512, you should end up getting 8. 8 times 8 times 8 comes out to be 512. So that would be your side length for the first cube. Let's say that these are all y's right here. So that means 1728 equals y cubed. That's how they got the 1728, is they did y times y times y right here. So again, we're going to do the cube root. And you're going to end up with y equals 12. 12 times 12, 144 times 12 would be 1728. So what's my scale factor? That's what we want to find out. What is the ratio of the two sides? 8 over 12. Is that a good scale factor? No, because it's not completely reduced. Scale factor should always be reduced. Let's divide it by 4. You're actually going to get a 2/3 scale factor. That would be a completely reduced scale factor. That means the area ratio would be 4 over 9 because 2 squared and 3 squared. So the ratio of their areas would be a 4 to 9 ratio. 2 cubed would be 8, 3 cubed would be 27. It would be an 8 to 27 volume ratio. That's how that would work out. Okay, good? Okay, last couple. For each pair of similar figures, find the ratio of corresponding linear measures, the ratio of the surface area, and the ratio of the volume. So here's what we want to do. We're going to put SF, because the first thing we want to do is find scale factor. Give me a scale factor for number 1. 2/3. How'd you get it? 6 over 9 would work, because then you could reduce that to 2/3. Or could you have used 10 over 15? Yes, this would have also reduced to 2/3. If it didn't, then they weren't similar. All the lengths have to reduce to the same ratio. So scale factor is 2/3. Now, what's my area ratio going to equal? Square them both. 4/9. Good. You're going to square them both. You're going to get 4/9. Okay, what's my volume ratio? 2 cubed is 8. 3 cubed is 27. 8 over 27. That's your volume ratio. Okay, let's look at this one right here, number 2. Find the scale factor first. Take a look at it.
3 over 8.
3 over 8?
No, wait, 5 over 8.
5 over 8?
Yeah.
If you did 15 over 24, is that going to reduce to 5 over 8? Yes, it will. 5/8. If you divide these both by 3, you get 5/8. That's my scale factor, so my area ratio is 25 is 5 squared, and 64 is 8 squared.
Yeah, I get the area ratio.
Okay, I did, to get the area ratio, I did 5 squared over 8 squared. Square the top one, square the bottom one, that gives you your area ratio. To get the volume ratio, we're going to do 5 cubed over 8 cubed.
1.5.
Yeah, 125 over 512. That's going to be your volume ratio. And then the last one, or last two down here, for each pair of similar figures with the given volume, find their corresponding linear measures. Do you remember how we just did this one right here? We just cube rooted both of them, didn't we? So what we're going to do here is make this a fraction, and we're going to cube root them both to see what the sides would have been. And he's right. This one, cube root of 343 would be 7 times 7 times 7, and 512 we already know is 8 times 8 times 8. So the cube root here of these two would be 7/8. All right, for this last one, let me move this up so you can see it. We're going to take this right here, and we're going to reduce it. What can we divide it by? Okay, want to try 4 first?
Yeah.
Okay, so let's divide those by 4. So 384 divided by 4, I get 96. And then 1296 divided by 4, 324. Can we reduce it some more?
Yeah.
Should we try 4 again? So 96 divided by 4, you get 24. 324 divided by 4, you get 81. Can we reduce it any more?
Yeah.
By 3 this time. So we should have done 12 on that last one, huh? So 24 divided by 3 is 8, and 81 divided by 3 is 27. Now this is my volume ratio. How do I get the side ratio? You cube root them. So what am I going to get? You're going to get a 2/3 scale factor. So your scale factor here would come out to be 2/3. Because you could reduce your volume. Now why didn't I reduce these?
Yeah.
Well, A, because they really couldn't be reduced. And B, they're already cubes. So you could cube root them right away to get those numbers. But this one, we have to reduce this down so that we can get cube to be able to cube root them. So we reduced it, so we could find what the two sides would have been, or what the two sides would reduce to.
Can't you use like cube root there?